Evet, evet. Onu kullanacağız zaten şimdi. Okay, so let's see how this. A linear map, right? A linear operator. This defines an operator like this, and dimension of V is equal to, let's say, n, and define a map. Okay. Map is defined like this. And wedge of V. How it is defined? From and product of V, extended product, to and extended products of V again. Okay. Given by now, what's a typical element of this? This is one-dimensional, right? This is one-dimensional, and the product of D is one-dimensional because so here n is dimension of D, and what's the basis for this? The basis for this is just if you delegate this E1 to En for D, then this is one-dimensional, and this thing is just span of this vector E1 up to En, right? This is the only vector actually in this vector space. You just take multiples of this one. So we define it this way. In general, of course, you don't have to take this basis element. A typical element of this is this one: V1 wedge, V2 wedge, Vn, right? I define it this way. So this is just T of V1 wedge, T of V2 wedge, T of Vn. This is the product of also n vectors that will be an element of this guy. Of course, you may define anything you want, but you have to show that it is a well-defined object. So, question is it well-defined? İlk önce şey göstereyim. Let me just maybe use this fact. I mean, if it is well-defined, then why gives us the result we are looking for. Okay, now first let us finish the proof. Finish the proof. Let us finish the proof using assuming that this map is well-defined. Nasıl yapabilirim? Well, I have two elements here, E1 wedge En, and I have E1 wedge En prime. But this is a one-dimensional vector space. Therefore, this element and this element are just a multiple of each other for some C. For some C. Well, then, ben ne göstermek istiyordum? T, E1 to En ne şeyler aynı olacak. Okay, now, all right. Now, lambda n power E1 which En. What is this? This is by definition T E1 which En. So it is just okay. Ne dedik buna? Lambda ama şey diyeyim. Neyse lambda diyeyim. E1 En. Buradaki lambda neydi? Lambda determinant of A. A de matrix representation of T in the basis data. And what about this one? E1 prime, En prime. Well, this is T E1 prime, H T En prime. And this is just some, again, lambda prime, E1 prime, En prime. But lambda prime is just determinant of A prime. A prime is just matrix representation of T in the basis beta. And our aim is to show that this lambda and this lambda are the same. Değil mi? Bunu gösterdik. Ama onu gösterdik sayılır. Neden? Okay, how can we show this? Well, okay, now T of şöyle diyeyim. Lambda prime nedir? Lambda prime is just this expression, right? Lambda prime is just T of E1 prime, H T of En prime divided by E1 prime, En prime, right? Lambda prime. Here, you have to be careful about this notation. You don't divide a vector by a vector. But we know that this is a one-dimensional object. This is, we are in a one-dimensional vector space. Therefore, any two vectors are multiples of each other. And this is not zero. Therefore, this thing is just a multiple of this one. So, you have to be careful when you write this. Okay? Nevertheless, this thing is equal to what? This is just this gadget applied to E1 prime, En prime, divided by E1 prime, En prime. But what is this element? Ya da şöyle diyeyim. Okay. Do this. Prime'ları sileyim de. Prime'ları sileyim şöyle. Okay. So I have lambda. But what is this gadget? That is just T times this. So this is T times E1 wedge, En wedge. And that is divided by E1 prime, En prime, C, because this vector is just C times this vector. So lambda is equal to, well, we know that C can be taken outside because this is a linear map. Okay. right? This is the linear map, therefore I can take C outside. So it's just C times this. And this is just C times C1 prime, Cn prime. Now C's are cancelled. I have this gadget. Divided by this digit. But what is this? This is by definition T on this vector. So T1, TE1 prime, and so on, TEN prime divided by E1 prime, EN prime. But what is this digit? This is just, so these are equal, therefore that is just lambda prime. So this is just lambda prime. Okay. Efendim? Kanıtlamadık işte, kanıtlayacağız onu. First, let's finish the proof, assuming that this is well defined and linear. Tamam mı? Okay, now let's see why it is well defined and linear. So,
şura lambda diye böyle falan yazdım.
evet.
Onların sebebi bu buradan oluşturduğu şey Van Dimensional tabii olduğu için.
One dimensional vektör uzayı olduğu için, evet.
Tersi de var.
Yani evet, vektör uzayı olarak K'ya izomorfik ama K aynı zamanda field olduğu için hani onun özelliğini kullanıyor. Bu kötü bir yazım ama hani ne kastettiğim değildir. Tamam mı? Bir boyutlu vektör uzayındasınız. İki tane vektör varsa biri diğerinin katı. Ben de o katını kastediyorum. Yani bunu uzun da yazardım da gerek yok. Bir boyutlu olduğu için. Tamam mı? Şimdi ne göstermemiz lazım? So, to finish the proof, must show this thing is well defined. And well defined'lığa bakalım. Şimdi well defined'lık için ne gerekiyor? So, how did we define this on a element like this? We define it this way. I apply T to first vector and then to the second vector and so on. What do we have to prove? Well, this same element has lots of different representations, right? If you have, actually, you know, if you choose randomly n vectors, their product is almost the same as this one, up to a scalar. Şunu göstermem lazım. We have to prove the following. These wedge products are defined using some axioms. What were they? We regard something like this, right? As minus V1 wedge V2 and then Vj, Vi, Vn, right? This object satisfies this rule for any ij, for any I different than J. If I interchange any two of them, then you pick up a minus sign. And it is linear in each component. What do we mean by that? Actually, it is, once you assume this, it is enough to show that it is linear in the first component. So we mean this. Lambda V1 plus V1 prime, dash V2, Vn is the same as this schedule. Lambda times V1, dash V2, dash Vn plus V1 prime, V2, dash Vn. Right? So these two elements are the same, and these two elements are the same. In other words, this element has two different representations. Actually, it has infinitely many representations, but each any two representations are obtained from this by applying finitely many such operations. Yani iki tane aynı elemanın iki farklı gösterimi olabilir. Bu gösterimler nasıl elde edilir birbirinden? Bu işlemleri sonlu defa uygulayarak, yani iki tanesinin yerini değiştiriyorum. Birini toplam şeklinde yazdıysam onu açabiliyorum. Değil mi? Bunlar başka bir şey değil. So what I have to show then, I have to show that this map respects, this change of representatives. So if I use different representations, I get the same thing. Let's see if it is the case. Yani tabii şurada aslında şöyle yapmamız lazım. Any element of this has this form, but in general, maybe you should say we have some summation like this, right? And same thing here. So finite sums of this, but don't worry about it. Yani bir tanesinin görüntüsünün ne olduğunu biliyorsam, toplamların görüntüsünün ne olduğunda tabii ki tarif edebilirim. Şimdi şuna bakalım. Şuna A diyeyim, şuna B diyeyim. A'la B'yi, so let's see that our map sends this element and this element to the same thing. How can we see that? Well, this gadget applied to this one, V1, V2. Here I have VR, and then I have VJ and Vn. What is the definition of this? It is defined to be this one, TV1, which TV2, which TVR, which TVJ, which TVN. But I know that since these are also batch products of elements, if I interchange any two of them, I pick up a minus sign. So I have this TV1, TV2, which TVJ, which TVR, which TVN. But then what is this? It is just minus. What is this gadget? Well, this is just again this gadget. So and exterior product of T applied to the vector V1, which V2, which Vj, Vi, Vn. So what happened? This element and this element are inverses of each other, and if I apply T to them, I obtain the same thing. Therefore, this gadget respects this relation. Değil mi? Yani bu eleman ve bunun eksilisi aynı yere gönderiliyor. Yani isterseniz eksiği şuraya da alabilirim. Bir de şunu kontrol etmemiz lazım. B1 pardon. Lambda B1 plus B1 prime which V2 which Vn. Now, what is this? This is just okay. By definition, T of lambda V1 plus V1 prime, which T of V2, which T of Vn. But what is this? T is a linear map, therefore, this is just lambda times TV1 plus V1 prime, which TV2, which TVN. However, I have this, this product distributes over this addition, and I can write this as lambda times TV1, which TV2, which TV, and plus this vector. Of course, I have T, right? T1 prime. I apply T to both of them. So I have T1 prime, which T2, which TVN. So what happened? Final line, şöyle yazayım. Bu da ne eşit? So let me just so this is just okay, lambda times this gadget applied to V1 which Vn plus this gadget applied to V1 prime which Vn prime Vn. So what we see is that yani şunu görmüş olduk. Bu eleman bu ikisinin toplamı bunun görüntüsü bunların görüntülerinin toplamına eşit. Bunu göstermemiz lazım yani. Peki. Dolayısıyla and actually this also shows that I guess this is a linear map, right? I mean, you can just linear olduğunu ayrıca göstermeye gerek var mı? Orada şöyle söyleyeyim size exercise. Yani buraya yazdığımız şeylerden sanırım o doğrudan çıkar. Peki, consequence of this, isterseniz bir tane örnek gösterelim. Ya da şöyle bir şey yapayım, proposition. If T1 and T2 are operations. Then determinant of T1, T2 is the same as determinant of T1 and determinant of T2. Of course, these are just elements of the field. Therefore, I can write it also like this. Burada ikisini yer değiştiremem ama artık burada değiştirebilirim. Çünkü bunlar field'ın içinde sarılar. Ve aynı şekilde madem bu buna eşit, bu da determinant of T2. Tamam mı? İspatı da gayet basit. Okay, now, so V is, let's say, span of this basis, E1 up to En, okay? It's a vector space of dimension n, and suppose it's the basis. Then we know what? We know the following. T1, okay, now T2 applied to this basis is what? This is just determinant of T2 times E1 which En. Okay, well, then what is E1 of T2 of E1 which En? Now, this is just T1 of this real number, I'm sorry, field element, right? This is a field element times E1 which En. Now this is just E1 composition T2 applied to E1 which En, and this is equal to what? This is an element of the field. It's a scalar and it's a linear, so I can just take it outside. So this is just determinant of T2 times T1 of E1 which En. But what is the last line? What is the last line? So T1, T2, E1 which En is just the determinant of T2 times this gadget. But what is this? Right? What is this? This is just the determinant of T1 times E1 which En. And what is this? Well, this is a linear operator applied to this gadget. Therefore, this is also equal to the determinant of E1 times T2 times E1 which En. So, this basis element times this scalar is equal to this basis element times this scalar. This is a non-zero basis element. Yani aslında orada sabit gelmiş. But we can assume for a while it's non-zero. So we are in a one-dimensional vector space. This thing is a basis element times this number, and that's equal to same basis elements times some other scalar. So these scalars are the same. Therefore, determinant of T1 and T2 is just determinant of T1 and determinant of T2. Okay. Now let's see one example. Efendim? Söyledik, ispat etmedik. O yüzden söyledik, istediğim ve ispat etmedik. Onun için bir başka şeye daha ihtiyacımız var. Bunu erteleyelim. Okay, let's do some examples. Let's say T is this linear map from R3 into R3 given by T, X, Y, Z. So I take a triple and let's say send it to the following. Minus 3x plus y, z plus 2y, and x minus y plus 4z. Okay, let's find its determinant. Determinant'ı iki türlü bulabiliriz. First, I take a basis for R3. First method, take a basis for R3. Hangisini seçelim? E1, E2, E3 değil mi? Standart basis. 1, 0, 0, 0, 1, 0, 0, 0, 1. And then write its matrix representation. What is TE1? 1, 0, 0. What is this? This is minus 3, 0, and 1. So it is minus 3E1 plus E3. What is TE2? 0, 1, 0. Yani 1, 2, eksi 1. Yani ne bu? E1 artı 2, E2, eksi E3. And T3 is just 0, 1, 4. Yani E2 artı 4 tane E3. Ondan sonra da T'nin matrisini yazıyorum. In this basis. What is this? Minus 3, 0, 1, 1, 2, minus 1, 0, 1, and 4. So determinant of T is just determinant of this space, this matrix. Okay. Bunu da hesaplamayı biliyorsunuz. This is one way. The other way is the following. We can use our, more conceptual definition of determinant using exterior products. Okay, so let's just look at this. T, E1, wedge, E2, wedge, E2. Okay. Not T, sorry. I am in 3 dimensions, so I have to take its cube, right? And what is this? By definition, this is just TE1, wedge, TE2, wedge, TE3. All right. What is TE1? I already computed it. It is minus 3E1 plus E3. Wedge TE2, it is what? E1, wedge 2 E2 minus E3, wedge E2, wedge 4 E3. Efendim?
E2 artı 4
Artı. Peki, ne yapabilirim şimdi? Evet, yani bir sürü terim var tabii de. Neyse bakalım. Şimdi şuradan başlayabilirim. Eksi 3 E1. Buradan E1'i alamam. E1'i alamayacağım için 2 E2 eksi E3 alacağım. Buradan da zaten E1'i alamıyorum. E2 artı 4 E3. Bir de ne var? E3'ü alabilirim. I can take E3. But if I take E3, then I don't have to take this E3 because E3 times E3 will be 0. So I can just take E1 plus 2E2. Burada da yine E2 plus 4E3. And what is this?
E3'ü alamayız.
E3'yi de alamayız. Evet, çok güzel. Sadece E2 kaldı. Evet. O zaman ne oldu? Şimdi bakalım. Buradan şunu alırsam, buradan sadece bunu alabilirim. Nedir katsayılar? Eksi 3, 2 daha 6, eksi 24, değil mi? Minus 24. E1 wedge, E2 wedge, E3, right? E1 wedge, E2 wedge, E3. What else? I can choose this one, E1, and then if I choose this one, then I have to choose this one. Ne eder bu da? Eksi 3, eksi 1 daha, artı 3, artı 3. Artı 3 ama E1, E3, E2. O yüzden ona da bir eksik koyacağız. Çarpı bu. Burası bitti. Buradan ne gelecek? Buradan E2 alıyorum. Buradan E3 alıyorum. O zaman buradan sadece E1 alıyorum. Değil mi? Başka yok. O da E3, E1, E2. Şunu bir buraya kaydıracağım. Bir de buraya kaydıracağım. 2 tane atlatacağım. 2 tane atlatırsanız değişecek. Artı 1. So it is what? Minus 26. Okay. Efendim? If you compute this determinant, you should get the same thing. Bakalım. Minus 3 times, right? Minus 3 times determinant of this. 8, 9. 3 kere yani 9. 0 gitti. Bir de ya da buradan yapalım. Eksi 1 çarpı şöyle yaptık. 0, 1, 1'e 4. 0, eksi 1. Eksi 27 artı 1, eksi 26. Okay. Anlaşıldı mı? Okay. More properties of determinants. Okay, now more properties of determinants. Okay. Şimdi A bir matris olsun. I wanna consider its determinant. So if I write B1 to be this one, A11, A1 and Bn. Yes. B and A and 1 B1, A and B and ne biliyorum ben? Okay. Define the following linear map. Evet. T map işi olsun. Define from and T1 B1 T Bn olsun. Tamam mı? O zaman ne biliyorum? I can define such a map. I'm just defining all the basis elements. Then we know what? T of E1 and exterior power of T applied to this basis element is just what? It is just determinant of T, and it is just okay, E1 H N, but I know that this is also just determinant of matrix representation of T in the basis. Burada tabii ki bu nedir? T'nin değil mi? Matrix representation in the basis beta. Why is that? Because first element is just B1.
B1 would be the top, would be the row, right? Change A, B, R,
Yeah.
R,
Yani şunlar evet. Bir N1. Burası bir N. N. Kalınlarla değiştireyim. Tamam. Yani bu aynı zamanda determinant A çarpı E1 N. Şimdi buradan ne yazabilirim? Tahtayı değiştirmemişim. So we take a matrix and some arbitrary vectors. Well, not arbitrary vectors. I define these vectors, and that is nothing but the matrix representation of this linear map. Sending I basis element to VR. Okay, now I know the following. Okay. Yeah. Şunu yaparsak, so if I interchange, let's say E1, ER, EJ, EN. What is the result of this? On one side, it is nothing but bir dakika. Yani ne demek istiyorum ben? Matrisin satırlarının yerini değiştirirsem ya aslında şuna hiç gerek yok galiba. Şöyle yazsam buradan çıkacak. Bunlara hiç gerek yok. Şöyle diyeyim. Şimdi determinant A nedir? Şunu gösterdik zaten. V1 Vn değil mi? Determinant A çarpı E1 En. Bunu gösterdik. Evet. Buradaki A da nedir? Bir yerde bu V1'in beta'daki şeyi değil mi? Kalımı. V2'nin kalımı. Vn vektörünün. Bunların basis'deki koordinatlarını kalım olarak yazdığım zaman elde ettiğim matris. Şimdi ben Buradan iki tanesinin yerini değiştirirsem, so this is minus, okay, let me write this here. V1, Vi, Vj, Vn. So if I interchange two elements, V1, Vj, Vi, Vn. Okay, then of course, so
Aynı şey.
bu ikisi aynı şey. So I have determinant A times V1 ve Vn. But this gadget also, if I write this, okay, so here replacing I and j elements corresponds to what? Replacing I and j columns, right? I and j columns. So if I interchange these two, I interchange these two columns. So this thing is also equal to determinant of a prime being E1 with En, where E prime is obtained from A by interchanging I and j columns. So what we see is that what is the relation between these two?
Onun eksisi olacak. Çünkü şu,
Ha, şuraya eksi bu.
o içerideki eksiz halinin determinantı. Yani ağzı, kavrayın. Değiştirilmiş hali.
Şimdi bu eleman buna eşit, değil mi? Bu buna eşit. Ha, şu ifade buna eşit.
Evet.
Eksi koyduğum zaman eksi koyacağım. Tamam. Dolayısıyla da ne ediyoruz? Determinant R prime is equal to determinant no minus determinant A. So if I interchange two rows, sorry, columns, I obtain minus sign. Evet, onu da şöyle diyeceğiz. Burada kalınlar için yaptık, yollar için de geçerli. Why it is true also for rows? Well, we proved actually. Okay, şunu gösterdik. In the beginning of today's lecture, we have shown what? We have shown the following. Ne yaptık? Evet, şunu yaptık. Sigma Sn sin sigma A 1 no sigma n sigma 1 1 sigma n to show that this is the same as A 1 tau 1 and tau n, right? We showed this. Well, if you look at this two here, you pick an element from the first column, and then you pick an element in the second column, and so on. But here, you are picking elements from first row and then the second row and so on. What does this mean? You are just replacing columns and vectors. So if this is determinant of A, This is nothing but determinant of A transpose. Değil mi? Kalınlarla row'ların yer değiştirmesi. Başka bir şey değil. Aslında şöyle görebilirsiniz. There is a very nice way of seeing this. Determinant is what? Determinant is this. From each row, you pick an element, right? But you don't pick the same element in the second row. So if you choose second element here, you have to pick another one, and then another one, and then you multiply them and put a sign in front of them. But just, rotate this picture 90 degrees, what you get. Instead of picking one element from each row, you pick one element from each column, right? Distinct elements, and then you multiply them and so on. So if you just rotate this figure 90 degrees, you just replace columns and rows. But the result will not change. Instead of picking elements from rows, you just pick elements from columns, and then you multiply them and add them up. That's why determinants of A head and A are the same. Gibi bu, M çarpı N'ye niye eşittir? Biliyor musunuz ispatı? Evet, değil mi? Bunu şöyle görebilirsiniz. Yani bu M çarpı N. M tane şey yazıyor. Yani mesela atıyorum 3 çarpı 2, 2 çarpı 3. 3 tane şey yapıyorum. Evet, şöyle. Bunu 90 derece çevirin. Çevirdiğiniz zaman nokta sayısı değişiyor mu? Değişmiyor. Burada kaç nokta varsa burada o kadar nokta var. Burada ne kadar nokta var? 3 tane 2 nokta var. Burada 2 tane 3 nokta var. O yüzden ikisi birbirine eşit. The same idea, okay? So this product is equal to this product. Same idea. Tamam mı? Tabii bu neyi veriyor? This proves what? This proves that any game you play with rows, you can play with columns and vice versa. And so if you interchange two rows or columns, you will pick up a minus sign. And if you add one column to the other one, you see, V1, which, let's say, V2, which here I have VI, and then here I have VJ, but let's add this digit here, VN. So what I did, I added ith vector to j vector after multiplying with a number. But when you open this up, since we have VI here, right, it will kill this guy. Therefore, this is nothing but V1 with Vn, the original product. What does this correspond in matrices? It corresponds to the following. Determinant of, let's say, some, okay, suppose this is the row 1, row 2, row n. This determinant is the same as this one. Row 1, here we have row I, let's say, and here we have row j plus number times row I, and then row n. Right? This operation corresponds to something like this. We take ith row and add to jth row after multiplying with a number. Okay, but that doesn't change the determinant because in vector products, this means you replace Vj by Vj times lambda times Vi, but this doesn't change the product because we have the item. And of course, we can play the same game using colors. Right? Son bir tane soru sorayım. Bunu da salı günü yaparım size. Güzel bir soru. Efendim? Today's lecture is included, but Tuesday I'll just answer your questions and do some more examples. I will not do anything new. Let me give you an exercise. Show that determinant of this matrix. Let's say 1, x1, x1 squared, xn, no, x1 to the power n minus 1, 1, x2, x2 squared, xn to the power, no, x2 to the power n minus 1, 1, xn, xn squared, and xn to the power n minus 1. Determinant of this is, şimdi kafadan atmayayım da, evet, şunu işte, x I minus xj'lerin çarpımı, bir c I, bu kesin büyük, n eksi 1. Yani ne demek istiyorum? Şu. Determinant of 1, x1, x2 ise bu nedir? x2 eksi x2. Determinant of 1, 1, 1, x1, x1 squared, x2, x2 squared, x3, x3, yok, evet, squared. This is just x2 minus x1 times x3 minus x1 times x3 minus x2. Okay. Efendim? Evet. Uygulayabilirsiniz. Evet. Ama o yani burada hopeless bir şey. Burada yani bu çok kolay değil. Bunun ismi de var. Van der Mondt galiba. Pi product. Summation değil de. This is not summation but product. You multiply all these terms. Right? How many terms do we have? And choose two terms, right? Yani i'ler j'lere bakıyorsunuz ama biri diğerinden küçük. O yüzden and choose 2 bölü 2 mi? Burada mesela 3 3'ün ikilisi 3. Tamam. Okay, let's stop. Bu koymuş.